Great. Welcome to the third place OTTO multi-object recommender system winners call. Andreas, I'll turn it over to you for introductions on the OTTO team.
Hello, everybody. My name is Andreas. I'm the product owner in our Tesla team. This is the team at OTTO that develops recommendations, mostly real-time recommendations. And today we are with Philip and Sophie. They are data scientists. Maybe Timo, our third data scientist, will join in a few minutes. Christian is our technical lead, and Paul, Wesse, I hope I don't forget somebody, Tobias, are developers in our team. If I forget somebody, please excuse. And we are very excited about learning about your solution and your findings, and hope this will be a very informative and fun hour for all of us.
Great, so you can go ahead and start.
Okay. Let me share my screen first. Can you see my screen?
Yes, we can.
Nice. Let me maximize it. How I do that? Yeah.
Oh.
Still seen?
Yes. Yes.
Good. Good. So thanks everyone for attending the call. Here I'm going to present the third place solution in the OTTO Kaggle competition. Our team is 4 people. It's me. My name is Giba, and also Benedict, Chris, and Theo. So the agenda for today, I will cover some basic steps on our approach on the competition. So basically, we are going to talk about the co-visitation matrix, an important piece of our solution, then some feature engineering and training methods, and we will end with some important findings, followed by questions and answer. Okay, so basically this is our team. We are all NVIDIANs. 3 of us, Theo, Chris, and I, comes from a team internally in NVIDIA called KGMON, Kaggle Grandmasters of NVIDIA, and Benedict is part of the Merlin team in NVIDIA. So we assembled this team basically by NVIDIANs, right? We are interested in promote recommendation system solution in all kinds of challenges. We participate also in the past in the Rexis challenge. We won some Rexis challenge, got very we all have some skill sets on recommender system, and we like to join this kind of competitions, right? Let me introduce a little bit of myself. I'm a data scientist, but I'm graduating in electronics, but I always loved computer science and that machine learning stuff. And I am early adopter in Kaggle. I've been joining competitions for more than 10 years. I think, Theo, you can introduce yourself, if you don't mind.
Yeah, so I'm Theo. I'm the newest KGMon guy. So been on Kaggle for maybe 4 years and been loving it. So glad to be here.
Cool. Also, everyone knows Chris Diot. He's also a grand fan of Kaggle and contributes a lot in the forums, in the competitions. But also we have the Benedict Schiffler. He's from the Merlin team internally in NVIDIA. And also Benedict works mostly with recommender system projects and libraries from NVIDIA. Okay, let's start with a quick summary about the competition. Basically, this is what we are looking to solve, the challenge here, right? So we have the recommender system from OTTO. We have user sessions. It's a big data set. I not say huge, but it's a big data set with more than 200 million engagements, 13 million users, and almost 2 million unique items in the data set. So you basically here to predict 3 different labels, 3 different targets for click target, cart target, and order cart, right? And I like to point here that click targets is a little bit different from cart and order targets, because for clicks, you are going to predict the next item user is going to click, right? It's different from the cart and orders that you are supposed to predict all the carts and all the orders each user will make in the future, at least in the future of the test set, that is approximately 1 week only, right? So this is basically what the challenge is, but I don't need to go into details here because I believe everyone in the OTTO knows what we're approaching here. So our main solution is based on 2 steps. Basically, we have a candidates generation and then a re-ranker model. Our candidates generation, basically, we are selecting or filtering a subset of items candidates for each user. Basically, we use a technique called co-visitation matrix to do that. And in average, we have 75 candidates per session or per user, right? So what do? We pick that candidates, that 75 in average, and we build a data set, and we run a re-ranker, what we call re-ranker model, in order to improve the recall at 20 metric for those candidates, right? We use a lot of rapids to do feature engineering because of the speed, and most of our models are based on XGBoost, and most of our experiments are based on XGBoost, I would say. And it's important to use GPU accelerate XGBoost here to have the speed necessary to get the results faster and run more experiments. I'll let Theo talk a little bit more about co-visitation matrix, then I will continue. Theo?
Yeah, thanks, Siva. So this is the part that Chris was supposed to present. So we'll try to do my best Chris Dillard impression without the accent there. So go ahead, Siva. So yeah, you're pretty much familiar with co-visitation matrices. Basically, the idea is quite simple. You take all the sessions and you look at pairs of items and you basically count them. And this is going to be a good matrices for recommending stuff that was seen together. That's the main idea, and going to be covering how to use that. And one of the tricks we use is because the data is quite big, right? So you don't want to spend your time computing matrices on CPU with pandas. So we moved everything to GPUs, which enable us to compute matrices in a few minutes instead of hours. So moving on. So yeah, that's basically how we use co-visitation matrices. So for each item in the session, we are gonna retrieve the most popular items according to co-visitation matrices. And this gives us already a quite good way to recommend stuff. Like if we consider the last item, which was click item 8632, we have the 3 most popular items according to co-visitation matrices, and we can recommend this. So that's the main idea, but actually we go a bit further in order to combine the coefficients. Go ahead, Jupyter. That's the main idea of using co-visitation matrices is items that appear first in matrices are going to be weighted higher. That's the weight W. Like the first item in the co-visitation ranking is going to be weighted 1, and then you decrease the weight. And also items that were seen last by the user have the most predictive value. So you want to give them a bigger weight as well. And then you sum everything and you've got pretty much your score for the candidates. Go ahead, Jiba. And one trick we used and a bit abused is like we can actually use different ways of incorporating the weighting of combination matrices. So the straightforward idea is, yeah, let's just forget about clicks. We know that these users purchase this and this item, and what is he gonna purchase or see next? So just weight cards and orders more than clicks on the matrix. Go ahead, Gilles. Another way to do so is only consider the last item. We know it's the item with the most weighting value. So what happens when we only consider this one? Go ahead, Gilles. So this one is the last order, same ID, but with orders. Next. We can also consider items seen during the last hour. Next. And yeah, Chris also worked on defining a thing which is the last real session. And it's basically clustering sessions on time. Like if a user has activity on Monday and Tuesday, you will use 2 sessions. And we can use only the last real session. Next. So this one is the items that brought the user to the website, which is also a cool ID. Next. This is the first item of the real session. Next. And yeah, next slide is going to be the last item of the real session. So that's different ways of using sessions to restrict the way you use computation matrices. Next slide, please. And already using these techniques with a different type of matrices, Chris already achieved top 50 without even training the model, like only using good matrices, good coefficients, and a rule-based model. And then on top of that, you plug his re-ranker, and I plugged mine as well, and we use Benedict's also, and we got flat-based basically. So moving on, yep, next slide, please. So I said Chris was using a lot of different matrices, which I have not talked about yet. I only discussed the way he was weighting matrices. And the thing is, when you compute pairs for coefficients, you can actually restrict the subset you use of each session to compute pairs. One idea is to use only items that are close in time, like for instance, with a difference of plus or minus 3 hours. We can also compute unidirectional computation matrices. And here, the idea is we want to predict items that appear in the future. Instead of having pairs weighting equally whether the item is first or last, we can only consider one side of the matrix. The idea is to decrease the weight in the matrix, considering how further apart the 2 items are. And again, this is quite intuitive. So just implementing it was a nice addition to the pipeline. Next, Jiba. This is another way of restricting the items. We can consider only the next item, only the next 2, only the previous item and the next one, and previous 2 as well. Next. And this is, yeah, another idea, which is maybe the most simple, but the most powerful one, is you can, when you build computation matrices, you can consider only cards or only orders or only clicks to cards or stuff like that in order to have matrices that will correspond to the target we want to predict. Yeah, go ahead, Jiba. And yeah, this is basically other ways to build matrices. We can consider subset of the data sessions with a lot of engagements, sessions with few engagements, and such IDs. So a lot of possibilities. And I think in the end, Chris experimented with maybe 100 matrices. We used 25, something like that in the pipeline, and it was already a lot. Thanks, Juba. Next. So we use coevitation matrices to generate candidates, but I also abuse other matrices Chris created to generate features. And the idea is going to be quite similar to what he did with the weighting, is that for each session, you're going to look at the coefficients in the matrices. For instance, coevitation matrix, it can be also item embeddings of the candidates and the item in the session. So you're going to take that coefficients, they are called M in the slide, and give them a weight. And the weight is going to take into account the type of the action, but also the distance to the end of the session. And then you aggregate, like whether it's min, max, or sum, and you get a ton of features which interact really well with the target and together. Thanks, Juba. Next slide. Yeah, this is just a small plot of feature importance, so it's not really easy to understand, but the main idea about the naming is first part of the name is going to be the similarity measure I use, and the next part is going to be the weighting. So, for instance, we have features using embeddings, and with similarity measure can be last. Last is going to be give all the weight to the last item. I have also popularity measures that are weighted using different ways. And popularity is just going to be how many times each item is seen during the week. Thank you. Next. So this is for you, right?
I can pick this one. Yeah. Here's a bit about feature engineering that Benedict made in his model. He basically used the same covisitation matrix idea to build the candidates. But the idea here is to split the fourth week and the training set into 5 folds, right? And there are different approaches from Benedict idea. Basically, when he handled the pipeline for his model, he handled 5 times. Why he do 5 times? Because the bagging approach, trying to reduce the variance of the results. So basically, we run 5 times each fold, right? And in his model, there are 4 basically different splitting for the train and validation part approach. I'm not going to enter in every idea, but here is the idea is, if you split in different ways the train and the valid fold, we can add diversity to the inference on the week 5 in the test set. That's the main idea here. Also, the feature importance by weight here, we can see some very important features, but basically he used 150 features per target. So 3 targets, he selected 160 features. And some important features here we can see, and the importance plot is related with some time difference, the first one, and some scores based on the 3 different target variables: the card, the click, and the order. Also, word-to-vec similarity played a big role here in the feature importance. His model used mostly word-to-vec from the embeddings. But plotting the importance by gain, we can see the feature importance change a little bit. What's the difference here? Basically, when we're developing a model, we plot the feature importance by weight first to detect which features have more interaction with each other. And then, based on the features that interact more with each other, we try to build more features based on that interactions. And finally, we plot the feature importance by gain to check the real gain each feature is given to each target separately. One of the features that help the model to improve, to boost the scores is features based on embeddings of a factorization machine. I'm not going to enter into details here, but the idea here is basically we built a data set, a new data set for a sequence to sequence model. So predicting the next item to click, and we run a factorization machine. We transform that data set in a binary classification. So we assign to 1 if the user is going to click on that item, and 0 if it's not going to click on that item. The idea is during the training, we build different training strategies to assign the negatives, right? Because we already know the positives, the items that user is going to click, but we don't know the items user is not going to click. So what matters here is how we define the strategy for the negatives. Basically, we find that using random negatives, using just the items that is found in each batch is enough to generate the negatives here and keep the target distribution. So basically, running a factorization machine gives us the embeddings and item embeddings, right? And those item embeddings were used in the models to generate more features for the re-rankers. Also, it's possible to use the embeddings to retrieve better candidates in the candidates generation step, right? We found that using cosinus similarity is much better than using any KNN algorithm. So basically, we can improve the candidates generation by using cosinus similarity on the factorization machine embeddings directly. Here, some curiosity. On the table on the left, we can see the linear coefficient of the items previously seen by each session. So basically, we can just prove here that the last item have the more weight. And for example, compare the last item clicked or saw by a user is weight 4 compared with 10 items before is 0.3 in terms of relevance, right? So basically the top 5 or last 5 or last 6 items seen or clicked are the most important when predicting the next item to be clicked. Also, in the image in the middle, we can see the hour embeddings. In the factorization machine, we added the hour of the data set, starting from the 0 hour of the first day in the train set, and ending on the last hour, the last day of the test set. We can see that the hour embeddings changes over time, showing that maybe user behavior changes, or maybe there's some promotions during the time, but during it's important to notice that the user behavior changes over time. And also on the right, some TSNE embeddings plot. So we decrease the dimension of the factorization machine embeddings and plot in a 2D representation. And we can see that are some patterns here, some curious patterns there, okay? Okay, some training methods here. One extra trick Theo made in this competition to improve the accuracy was to use the validation split also as an extra train session to augment the train set and generate a boost in the CV. So when we are validating here, basically we are picking the week 4 of the training set, and we split half with 50% randomness the sessions. And so basically half of the sessions become train set and half becomes validation set. So instead of the validation set be used only to build the targets, we use also the validation part of the sessions to augment the train set as extra sessions. And this little trick improved by 0.001 the CV and the leaderboard. It was nice. It shows that using more data can boost the accuracy of the models. In the TIO pipeline, is just an overview of the TIO's pipeline. Basically, TIO is working with week 4 to train the re-ranker, right? He split in 4 folds, grouped it by session. It's important to group by session here in order to work. He used that extra training sessions to augment the training set, right? Then downsample is important. Downsample helps the models to fit in memory, and at the same time, it helps to boost the accuracy. For example, remove sessions with no ground truth. Some sessions have 0 cards or orders. For example, we just can drop the sessions from the training folds. Also, we can resample the negative samples of the candidates, also in different probabilities. And for training parts, important to use GPU here. That's why we use XGBoost classifier. And another thing we use is use OTTO to tune the hyperparameters. And using GPU to train the model is important because we can optimize the parameter with the speed of the GPU provides in training those data sets. Also, for the inference, we use QDF. It's a rapid library that uses GPU to read the data frames. And we infer on GPU forest inference library. Is also forest inference is an NVIDIA Rapids library that promotes high-speed inference for gradient boosting models. Basically, forest inference picks a pre-trained model. It can be XGBoost, LightGBM, or CatBoost, or scikit-learn. It loads that pre-trained model and runs the inference directly on GPU to speed up the process. And here is important because we are inferencing millions of users on around 75 candidates each user, so speed is important here. Benedict train pipeline, there is a little trick here. I would say Benedict runs a bunch of features. He builds a bunch of features here, some based on transformers, some based on GRU, Word2Vec. But the trick here is the following. For the click models, he generates the candidates, then he generates the features for the candidates, and then he trains the XGBoost model. He does the same for the cards model, generate candidates, add features, and train XGBoost model. But for the order model, he used some scores provided by the clicks XGBoost model in order to generate more features for the orders candidates. We did it because the order is the target that have the more weight in the final metric. And also there's a hierarchy here. User usually first clicks, then add it to cart, and then order. And that's the idea here. If you have the clicks scores here, we can add as the order features for the training the order re-ranker model. The final solution is basically an ensemble of the 3 solutions. Basically, we assemble TIO model, Benny model, and Chris model here. How we do that ensemble? We pick the candidates generated by each one of these solutions. We rank by the most relevant item candidates to the less relevant. We assign a more weight to the most relevant item, and then we apply that weights we are showing here. 3 times to TIO model, 1 to Benny, 1 to Chris. Then we sort by the most relevant after applying that weighting, and we got that final leaderboard, 0.6382 on the private. Some interesting finds it help us to build our solutions is each session actually is a user session, and we found some patterns on the user sessions. For example, we have the hour of the day on y-axis and the day on the x-axis, and we can find some users. There are 2 users here, right, on this slide. We find that some users have some hour of the day patterns to search for items. it has some patterns of some days the user is willing to buy something or add to cart something, other days the user is not going to buy anything. But the idea here is we can find sub-sessions by just visualizing this plot here, and it helped us to build better features based on time. For example, we filter a user session in multiple sub-sessions based on the user behavior on these plots here. Rapid's TSNE also helped us to visualize some similarity between the embeddings and the user session. Here we can see a TSNE plot of one user full history of searching, right? We can see some groups of items embeddings that user are looking for are clustered in a very close space, depending on what user is looking for. Also, it helps us to build better features based on embeddings. Another curiosity is we use Merlin data loader to train the factorization machine, and embeddings. It speed up by a lot when computing. We reduce the training time by around 5 times by using Merlin data loader. Here's just another user example. One important thing to notice here is session-based recommender systems are a kind of sequential model, but they are different from natural language processing models. In natural language processing, we can see an example here, right? We have a sequence of words that usually doesn't repeat over time, but in Rex's it tends to repeat. The items tends to repeat. Is a sequence model, but in Rex's the items tends to repeat, and you observe the same behavior here in an OTTO data set. That repeating sequence we found in the data set worked here as well. I think I'm out of time. I just want to say something else here. Word2Vec embeddings are also valuable here. We improved the final scores local CV by 0.0004. It doesn't look much, but actually when you're doing Kaggle competitions, any decimal in the end is important. And when analyzing the embeddings, it's important to plot the distribution of embeddings in the train set and the test set to check for different distribution shifts. If you observe some big distribution shifts, probably that embedding is not going to work well on the test set, or probably something happened in the test set that leads to the shift. So it's important to try to identify this. And Theo also already commented about the single model solution. Actually, I want to point out here, because it was a great solution Chris found in this competition. Basically, if we take that simple solution here, it can reach 97.7% accuracy of our final model assembly. So it's just 2.3% away from our best ensemble. But the idea here is we don't train any model. We just use the Chris 20 co-visitation matrix to build the candidates and pick the top 20 candidates per target. So to build the co-visitation matrix on GPU takes like 20 minutes. It's pretty fast. And that's it, 20 minutes to train all the models and to build the co-visitation matrix, right? Because just building the co-visitation matrix, it's the training process in this single model solution. Then applying the co-visitation to the user sessions for running the inference takes another 10 minutes. And it achieves 0.59 in the leaderboard. It's pretty high. I'm pretty proud of this solution here because it's pretty fast. Okay, I think I'm done with the presentation, and now I'm open to Q&A.
Yeah, thank you very much for the great presentation, and thanks again, or congratulations again to your great solution in the end. We have some questions prepared.
Sure.
I would like to start. You already mentioned like a simple model that doesn't include any machine learning at all, but we were wondering, since we're obviously interested in bringing the ideas to production, what kind of minimal viable model you would recommend from your solution. So like an optimal performance complexity trade-off out of your solution. So maybe selecting like the best models and the best features. What would you recommend?
Okay, so if you're looking for a simple solution, I recommend picking Chris co-visitation matrix notebook he posted in Kaggle. Basically, he used one co-visitation matrix per target. It runs pretty fast, and it achieves, if I remember correctly, 0.56 in the leaderboard. It's 3% lower than this single model here using 20 co-visitation matrix. So imagine you can run a co-visitation matrix in a couple of seconds, maybe less for 1 minute for sure. But with that co-visitation matrix, we can achieve like 0.56 in the leaderboard. This is the minimum, I would say. And co-visitation matrix basically use the idea of if user click one item, which other item user also clicks in the same session, right? That's the idea of co-visitation matrix. And yeah, I will start from a single co-visitation matrix and see what it does.
Okay. Yeah. Actually, co-visitation, we're using exactly these recommendations for the recommendations, since they're working so good, as you also discovered.
Nice. Nice. Can I ask you, did you start using co-visitation before the competition?
It's like
or after?
The oldest model in our team. It's older than most of the team members, or has been longer in the team than most of the team members.
Older than first membership.
And we tried a lot of methods to beat it with machine learning, and it's hard, as you have seen.
Yeah. We tried also a bunch of other deep learning methods, but no method beats the co-visitation matrix plus gradient boosting.
Yes. Regarding those gradient boosted methods, did you also try any other re-ranking models except for gradient boosted trees?
We try some neural-based re-ranker. After the competition ended, we tried cat boost also.
Did that improve your results?
Yeah, after the competition, it improves a little bit our results using cat boost instead of XGBoost. But there's a very specific configuration of cat boost to make it work correctly. But yeah, it beats by a little bit.
The one that was mentioned by the second team solution,
exactly. But probably blending, if you have time, blending XGBoost, LightGBM, and cat boost will provide even better results.
Yeah, probably something like that wouldn't be practical for the production system, but it definitely helps in the leaderboard.
Let me talk. We tried neural network for the re-ranker, but it didn't perform so well as gradient boosting.
Yeah, we heard that from other teams as well.
Yeah.
How did you select the final? Because you mentioned like Chris calculated hundreds of co-visitation matrices, and how did you go about selecting the best matrices? And also, were there specific weights for the different matrices, or were they all weighted the same?
No, we ran a bunch of experimentation here. We use that advantage of GPU speed to calculate the validation scores quickly, right? So we can iterate between this experimentation, but basically we try some weights by hand, I would say. For example, we increase the weights of one of co-visitation matrix and run an experiment. Then by hand, we hard code different weight and try again. And we try to have an idea of which feature are giving more boost to the co-visitation matrix candidates based on recall at 20 metric, right? So yeah, basically we iterate over a bunch of experimentations very quickly and trying the weights of each co-visitation matrix differently. And we use a lot of intuition also when blending the co-visitation matrix, but basically experimenting a lot and try to handpick the best weights and the best strategy to blend the co-visitation matrix to generate better candidates.
Mm-hmm. And for selecting the matrices, you looked at the CV score, probably.
Yeah, we rely on CV score and the leaderboard score. Basically, from time to time, we have the CV score and we submit to leaderboard. And we compare if the boost we get on the CV score is the same boost we get on the leaderboard score, just to confirm that what we are doing is not overfitting and it's working. That's the main idea. Yeah. That's why it's important to keep a validation data set fixed and have some holdout set also to just confirm the scores. Yeah.
Yeah. All right. In the write-up of Benedict's solution, I saw that he was also using transformers for rec for candidate generation.
Yeah,
Did you end up using that in the final solution, or was that just an experiment?
No, he used mostly for candidate generation and also to build features. He used some transformer for rec scores and the embeddings generated by transformers for rec something. Yeah, to add as a feature for the re-ranker.
And that gave a boost versus just using Word2Vec.
So did he use the
item he used both.
Did he use the item embeddings or the time embeddings in the output layer?
For which model specifically?
From transformer for rec, you said that he used the embeddings. I don't know which embeddings you mean. Or
I believe, I'm not sure. I'm not going to say exactly here. I just saying what Benedict told me. He used some embeddings. Probably he extracted the last layer or something like that.
Okay.
Yeah.
I think he used the item embeddings.
Item.
And then similarity, yeah. Like first layer is
he didn't use the session embeddings from the transformer, so only the items.
Just
I don't think so.
Okay.
Yeah, I'm not sure as well.
Yeah, we'll have a look in the code. We'll see.
Yeah, I run some experiments with factorization machine session embeddings, and it improves all my local CV, but I didn't have time to try it on the leaderboard.
Oh,
but yeah,
it wasn't integrated into the pipeline.
Yeah, exactly. But the session embeddings were providing some boost if you use the session instead of the item. Yes.
Yeah, and the final question that I have written down here is, what was your pipeline computation time? I think you mentioned something about 72 hours. Is that correct?
Yeah. If you pick all the models, all the training times, all the candidates generation, everything, data per-processing, inferencing, from scratch, it takes around 72 hours.
Exactly. And what is the slowest part of the pipeline? What takes the most time?
It's hard to say. Yeah, go ahead, Kev.
Yeah, for my pipeline, I'm brute forcing OTTO, so it's quite slow. Like for each fold, I run 20 iterations of OTTO. Takes maybe 4 hours per fold. So since we have 3 targets and 4 folds, it's quite slow. But you can reduce that easily.
I see. So you used OTTO to optimize the hyperparameters for the tree?
Yeah.
For the trees? Okay. What hyperparameters were you optimizing?
Maximum depth, the regularization alpha and lambda. Not gamma. I don't tweak gamma. And the subsample of columns and rows.
All right. Yeah.
That's more important.
Great. Thank you for all the answers. Those were the questions that I have written down. Maybe there are some more questions from my teammates.
No, I just came a little bit in too late. But congratulations, I think this is pretty cool.
I think then we're ready to wrap it up. Thank you again
Okay.
for the presentation. And yeah, it was nice to meet you.
Thanks a lot.
Nice to
Thanks,
meet you all,
everyone.
guys.
Thank you.
All right.
Thank you.
Thank
Thanks,
you.